The pH and pOH scales. So pH is used to make hydrogen ion concentrations be more reasonable numbers, basically. And so here's just the pH scale before we tell you exactly how they come about this. pH neutral is 7. Acidic is going to have a lower pH, and basic is going to have a higher pH. And you should know that. You know, if I tell you, okay, this solution is a pH of 9, is it acidic or basic? Well, it's basic. So those are sorts of things you should know. So let's look at hydronium ion concentrations. So hydronium ion concentrations end up being these really small numbers, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. These are factors of 10. Okay, so 10 to the minus 3 is 10 times larger than 10 to the minus 4. So here they've given a representation. So this would be 1 circle, and this would be 10 circles, and this would be 100 circles. And so the variation of hydronium ion concentration goes from 1 mole per liter down to 10 to the minus 14 moles per liter. That's 10 orders of magnitude. It's huge, a huge range. And so it's really hard to deal with numbers that vary so tremendously. And so we use logarithms to compress and linearize scales like that. So what is a base 10 logarithm? Really need to redo these notes. Let's just go with, let's go freehand here. See if that works better. I'll make it look like chalk. Okay, so 10 to the second. We know that that equals 100. The log, the base 10 log of 10 to the second equals 2. The base 10 logarithm says what power of 10 is that number? That number is 10 raised to the what? Well, 100 is 10 raised to the 2. So the log of 100, or the log of 10 to the 2, is 2. So 10 to the third is 1,000. The log of 1,000 equals 3. Because 1,000 is 10 raised to the third power. 10 to the minus 2, 0. Blanking out there. The log of that is minus 2. Because 0.01 is 10 to the minus 2. You see how that works? It works real nice with factors of 10. And you get into numbers like 5, and then it gets a little more difficult. You can't just do that in your head. So when we have concentrations like at neutral pH in pure water, the hydrogen ion concentration is 1 times 10 to the minus 7th molar. While the log of 10 to the minus 7 is what? Minus 7. All of those concentrations for hydrogen are going to be 1 or less. And so they're all going to end up being negative numbers. Negative numbers are kind of icky. And so what we do is we say, well, let's just make that a positive number. So we do that by multiplying by minus 1. The negative log of 10 to the minus 7. That's not the anti-log. It's just the log with the sign changed. So the log of 10 to the minus 7 was minus 7, and we say, no, let's make it a positive number. And this is what pH is. pH is the negative log of the hydrogen ion concentration. So here the hydrogen ion concentration was 10 to the minus 7. The negative log of that is 7. Any questions? Your calculator has a button that does this for you. It's log. Has nothing to do with wood, it's log. So let's go back to the slide and see if that makes any more sense now.
What kind of wood does a mathematician burn? A natural log?
Very good. And natural logs are different than base 10 logs. Natural log is ln, and that has, instead of a 10, what power of 10, it's what power of e. And e is 2 point something, and we don't use that in chemistry much. That's more of a biology kind of a deal. So when we look at this now, we see that when the hydrogen ion concentration, and remember, hydrogen and hydronium ion concentrations mean exactly the same thing. It's just we get tired of writing the 3O in there, and we just do H plus instead. So the pH is 4 because the hydronium ion concentration is 10 to the minus 4. The log of that is minus 4, and then we change the sign, and so we get 4. And here we get 3, and 10 to the minus 2, and we get 2. And so this gives us a nice, manageable scale that runs from 0 to 14, and it's much easier to deal with than 1 to 10 to the minus 14. So pH is just a device that we have made up to make the numbers nicer. Okay. So explain logarithms. I just did that. I get ahead of myself. So let's see. Yeah, let's just do this again. So calculate the pH of each solution and indicate whether it's acidic or basic. So H3O plus, the hydronium ion concentration is 9.5 times 10 to the minus 9. We can't do this one in our heads. We need to use the calculator. So get your calculator out. Some calculators want you to press the log button first and then put in the number. In other calculators, you put the number in first and then the log button. I've got a TI-30XA, and I put the number in first. So I go 9.5 EE minus 9, and I press the log button, and it gives me minus 8.022, blah, blah, blah. And then I change the sign and make it a positive number. So the pH, yeah. Tell it to, there we go. I'm just having a discussion with my iPad here. So the pH equals the negative log of 9.5 times 10 to the minus 9. And, as we talked about with equilibrium constants, we don't worry about units here. Concentrations are always given in moles per liter, and then it all works out. And so I'm going to write this as 8.02, and that's the pH. pH doesn't have a unit. Were you able to get your calculator to show you that number? Does anyone need me to whisper to their calculator? Yes. Okay, let's do this next one. Hydronium ion concentration is 6.1 times 10 to the minus third. What's the pH? Well, the pH will be the negative log of 6.1 times 10 to the minus third. This is going to be 2 point something. So 6.1 EE minus 3 log, change the sign, 2.21. All of you with functioning actual calculators, can you get it to do that? Because that was a poke at you.
No, I don't understand.
Okay.
I don't understand why they don't give me that. It's just retarded.
Well, you may need to get an app for a scientific calculator.
I didn't pay my bill. I'm not supposed to get that.
Wi-Fi.
The problem is it's not an iPhone. That's the problem.
It is Samsung. It is
Oh,
an
that's
Android. And Androids are better than a crappy Apple.
Okay.
Hostile.
It's not free then.
I'm holding an iPad and I have an iPhone in my pocket. But I use a PC because the Mac computers, I don't know.
I'm a PC.
I'm a PC person. Okay, so devices aside, I want to talk to you for a minute about significant figures. Just because I guess it's a pet peeve of mine that a lot of people don't seem to understand how sig figs work with this. So let's say that instead of 9.5 times 10 to the minus, no, let's do this other one, 6.2. So instead of 6.1 times 10 to the minus third, let's say it was, oh, I forgot something, okay. Rewind. We didn't answer all the question. Is the solution acidic or basic?
For the first one, it's basic.
For A is basic, and the second one,
Very acidic.
acidic. Thank you. Okay, so we got to be complete. Okay, now on to significant figures. So I'm going to change color here just to make it look a little different. So what if the hydrogen ion concentration was 6.1 times 10 to the minus 11 molar?
It's
What's the
strong base.
pH?
It's going to be like
It's going to be 10.21. Check me. What if it's 6.1 times 10 to the minus 7? 6.21. So you're catching on. What if it's 6.1 times 10 to the minus, give me a number. 8.
7.21.
7.21. How the hell am I getting that? Pardon my French. Okay, so the exponent here shows up as the digits before the decimal point. This is not 11, it's 10. It's one less than this because this concentration is between 10 to the minus 10th and 10 to the minus 11th. And so the log of it is between 10 and 11. So this was minus 11, the pH is 10. Minus 8, the pH is 6. Minus 8, the pH is 7 something. The 0.21 is coming from this over here. In this scientific notation number, what are the significant digits?
2.
It's the 6 and the 1, right? It's 2 sig figs. The 10 to the minus 11th is just a placeholder for the decimal point, right? So where is this 6.1 reflected in the pH? Only in the 2-1. So this part is a placeholding thing, for lack of a better word. These are placeholding digits, essentially. And the significant figures come after the decimal point. So do you need to understand that to pass the class? No, but I don't know. I feel some inner thing compelling me to explain that to you just because someone needs to tell the world how sig figs work. Because I've encountered chemistry instructors who have no clue. So anyway, that's why I'm writing my sig figs the way I am. I'm not being sloppy or adding stuff or anything. I'm actually doing that. Anybody have any questions about that?
So when we put it in when we put that in a calculator, it'll be more than, okay.
If you put in 6.1 times 10 to the minus 11 and press the log button and then change the sign, it'll give you more digits than 10.21. But I'm rounding off based on the number of significant figures in the original number. So there won't be anything on the exam that will trick you and where you would have to understand this, but I know some of you have curious minds and would be wondering why this doesn't seem to make sense with the significant figures. So there it is, that's why.
With the 6.1 ending up as 0.21 and the 9.5 ending up as 0.02, I think me and Wyndham both have the same question of how is it reacting? You're just multiplying, and when it moves it out, it ends up being...
It has to do with being raised to a power.
Because that's like 0.00008.02, right? Because it's like a bunch of zeros power. It's to the negative 8.
No, I think when we go to the next step,
It'll-
it'll make more sense. So
I
let's,
just have a quick question.
Uh-huh.
Since the 10 to negative 11, since the 11 was a two-digit number, and then the number that you were multiplying was a two-digit number, that's why that one was 4, and then the other ones were 3?
no, this, oops,
Just ignore the number in front of the decimal and just round
Exactly.
it in times two.
the digits to the left of the decimal point are placeholders. They come from the exponent in the scientific notation. All the significant figures in a pH come after the decimal point. Okay, so they all have 2 significant digits. The one before the decimal point doesn't count.
Okay.
It's a placeholder. So hopefully I didn't confuse everyone. So how would we calculate the hydronium ion concentration if we're given the pH? So we know that pH equals the negative log of the hydronium ion concentration.
So it's gonna be like -9.
So we need to rearrange this equation and solve for hydronium ion concentration. Can we just divide by log on both sides? Log is a function, you can't divide by it. Let's get rid of that negative sign first. So I'm going to multiply this by -1, and I'm going to multiply this side by -1. Now I've got minus pH equals the log of the hydronium ion concentration. And I'm not going to test you on this derivation. How do we get rid of a function?
Multiply by its inverse, or do it?
You do the inverse function. Okay, so what's the inverse of log?
Exponent?
No, antilog.
Alright.
It's like matter and antimatter. It's log and antilog. Antilog is 10 to the x. On your calculator, on the log button, the other function is 10 to the x. On the ln, the natural log button, the other function is e to the x. So we do 10 to the x of both sides. So 10 to the pH minus pH equals 10 to the log of the hydronium ion concentration. And 10 to the log of something is just the something. So the hydronium ion concentration equals 10 raised to the negative pH. That's an equation you're going to want to write on your note card. So then to solve this problem, we want 10 raised to the power of, what's the 8.37. And then how do you do that on your calculator? Well, use the 10 to the x button. On my calculator, I put the number in first. I put in 8.37. I changed the sign to make it negative. And then I press the yellow button second to get the 10 to the x function. And it shows me this big old small number with lots of zeros. So I'm going to put it in scientific notation. And that's going to be 4.3 times 10 to the minus 9th.
Do you have to do 3 significant digits because the pH was given as 8.37?
I'm going to give 2 significant figures because only the digits after the decimal point are significant in a pH. We just talked about that.
Oh, that's right.
You didn't get that?
I guess I
Did you get .000000004?
did. Yeah, it was 4.
Okay, put it in scientific notation on your calculator. The rest of it's hiding. It's off the screen.
Minus it times -9 and then
It is times 10 to the
So,
minus 9.
Once we after all the zeros, once we got like 4 and 3, we already know it's gonna be -9 because we added 8.37. You add 1 and then make it negative, so that's how you know it's -9. And then the first 2 digits would be
Well, yeah, you can predict the 10 to the minus 9th
Yeah.
by looking at the pH.
and
But
then-
unless your brain does logarithms, You can't do the 0.37 going to 4.3.
Oh, no, I was gonna do that by calculator.
Yeah.
Just to skip counting all the zeros and maybe making a mistake there.
Use scientific notation. Yes, question?
Well, is it only 4.3 if there's two significant digits other than pH?
Because the 4 and the 3 are the two significant figures.
Oh, okay,
Yeah.
How do we put in scientific notation to formulate that?
I'll come and show you.
Page count.
So we talked about the pH scale, and now we're going to talk about the pOH scale. pOH is the same thing regarding the hydroxide ion concentration that pH is for the hydrogen ion concentration. So pOH is the negative log of the hydroxide ion concentration. And in some branches of science, they also talk about like p-calcium. P-calcium would be the negative log of the calcium ion concentration. So P just stands for negative log of, at least as far as I'm concerned. Okay, so there's a relationship between pH and pOH. That's kind of cool. So we know that the hydrogen ion concentration times the hydroxide ion concentration equals a particular number. Anybody remember what that is?
H2O?
H2O is not a number.
Oh, 10 to the negative 14.
10 to the negative 14. Goober. Okay, so this is another one you might want to write on your index card. So what if we took the negative log of both sides of this? Something bad would happen. The world might like self-destruct.
Equals it may. Clean up the
Crashing down.
Okay, so what is, when we take the log of numbers that are multiplied, then we add them. So this equals the negative log of the hydrogen ion concentration plus the negative log of the hydroxide ion concentration. And what's the negative log of 10 to the minus 14? It's 14, right? The log of 10 to the minus 14 is minus 14. Change the sign, it becomes plus 14. Negative log of H plus is what? pH. Negative log of hydroxide ion concentration is pOH. pH plus pOH equals 14. That looks just like too simple, doesn't it?
It is. Sneaky tiny.
Because it has to be 40.
It has to be 14. It's always 14.
Well, it's 15.
Nope. Because the equilibrium constant for the self-ionization of water is 10 to the minus 14. And if one goes up, the other goes down. If the hydrogen ion concentration is higher, then the hydroxide ion concentration is lower because it's in equilibrium and it shifts around and maintains that thing. Yes?
Is this equilibrium only for the pH of water? Or?
This equilibrium is for anything in aqueous solution, which is the only type of thing we've talked about and are going to talk about. So if it's in aqueous solution, pH plus pOH equals 14.
Would this type of concentration of up to 14 or negative 14 for either or, does that also apply like when they have like on, is it gamine that has like liquid sulfuric acid, but it's just super concentrated? Would that be considered like a 1 or a 0?
When you get to the much more concentrated acids, there's really not enough water in there for this to work. So I would have to think about, I don't know off the top of my head how this would apply to a concentrated liquid acid.
Oh, this is just them dissolved into an aqueous.
This is aqueous solution.
Oh, okay, well that's cheap.
So
Yeah.
it has to be at least 51% water to be considered aqueous? Or?
No, I wouldn't necessarily say that, but there is some limit there's some point
Yeah,
at
one drop of
which
water in a
it gets
whole-
messed up, yeah. Because there's just not enough water to do what it wants to do. So we're just talking about pH 0 to 14. So I want to show you something else that's cool.
I know there's a couple that something say that it's a hot day, if you count all your young cells die. And you'll never really take something in your days and you kind of research them.
Okay, so we've talked about several different things here. We've got pH, and we've got pOH, and we've got hydroxide ion concentration, and we've got hydrogen ion concentration. And they are all related to each other. We can convert between the hydrogen ion concentration and the hydroxide ion concentration. That was the first thing we learned how to do. Because those concentrations multiplied are going to equal 10 to the minus 14. Then we learned how to convert between hydrogen ion concentration and pH. pH equals the negative log of the hydrogen ion concentration. And the hydrogen ion concentration equals 10 to the minus pH. And we just talked about the relationship between pH and pOH. And then this is analogous to the pH H plus one. So pOH equals the negative log of the hydroxide ion concentration, and the hydroxide ion concentration equals 10 to the minus pOH. Isn't that beautiful? I love that. So is the circle. Given one of these quantities in the circle, pH, pOH, hydroxide ion concentration, hydrogen ion concentration, you can calculate all the others. Oops. So let's do an extra little example here. Come on, move. So let's say that the pH equals 7.4, which is the pH of your blood, by the way. What is the hydroxide ion concentration?
6.6.
No, it's not 6.6. The pOH is 6.6.
Oh, okay.
Okay, so pH, if we're given this, we're given the pH, and we're asked to find this one across the way. It's going to require 2 steps. But we can choose which direction. We can choose if we want to go this way, or if we want to go this way.
For the right way.
Personally, I do not like this guy down here. It's just kind of icky. And so I'd rather go this other way. I'll go pH to pOH, because this is so easy. It's just subtracting. There's no scientific notation or anything. Go to pOH and then do that. So Andrew's correct in that it's 6.6. So pOH equals 14 minus the pH. So that's 6.6. Now that we know that, the hydroxide ion concentration will equal 10 raised to the power of minus 6.6. So we can do that. 6.6. We had 2.5 times, well actually, that would only have one significant figure, so that's going to round to 3. This is 2.51, that would round up to 3. 3 times 10 to the minus 7 molar. Is that acidic or basic?
That's basic.
It's basic, but just barely. It's very close to neutral. Any questions? So those are all of the equations for pH. And then this example is kind of a letdown afterwards, but we'll do it anyway. Calculate the hydroxide ion concentration if the pOH is 4.25. So it's 10 to the minus 4.25. 5.6 times 10 to the minus fifth.
Because you're
pOH and hydroxide ion concentration are not the same thing. They're related, but they're not the same thing. Took me a minute to figure out where on earth is he getting that number.
I was running the second number though, like the second step for this situation.
If there was a second step.
Instead of going from here to here, you're gonna go all the way around the circle. Because we were already on this.
Okay, so I'm trying to find that.
This is just a one-step thing.
How'd you find it? Was it the net that's log on? They log into 4.25.
Anybody else have any questions? He'll figure it out. No?